device that uses electric field and electric potential energy and separation of charge to store charge, called a capacitor. And we define the term capacitance. We're in?
We're good.
Nice. For those just joining us on the video, we've just been reviewing that board over there that Emily's going to zoom in on, because we got a quiz coming up. Right?
Right.
Okay. So now we're talking about capacitors. That's what our last class was about. Capacitor is a device that uses these concepts to store up charge and hold on to that charge until we give it a way to discharge. So we give the charge somewhere to go. In a circuit drawing, it looks like this. It's representing the two parallel plates, the two parallel conductive plates that are separated by some distance and usually an insulator of some kind, to store up positive charge on one side, negative charge on the other, a difference in potential between the two, which stores up some energy, and that energy is stuck there until I give it a path that it can discharge through. I gave you the example of an AED as a possible application of a capacitor in a circuit. We define the term capacitance to say how good a capacitor is at its job of being a capacitor. Capacitors hold charge, and capacitance tells us how good it is at holding that charge. What are the factors that we take into account with capacitance? How big it is, and how far apart they are. So the physical parameters of the capacitor itself determine the capacitance, the output capacitance. The definition of what capacitance is, I kind of skipped over this. C is equal to Q over V, where Q is the charge on the plates, and V is the voltage difference across the two plates. Oh, I know what I was supposed to get, Emily.
What?
A marker. My markers are dying.
Here, I'll get Hope or Aiden to bring one.
Do you want it?
Sure. Ah, you rock. Thank you. That's two colors, too.
Two colors.
So capacitance is equal to Q over V by definition. That's what we call capacitance. It says if you can put a lot of charge on it, it's a good capacitor. If it takes a lot of voltage to put that charge on it, it's not such a good capacitor. So the bigger the Q is, the bigger the C. The bigger the V is, the smaller the C. Q equals C equals Q over V. Yeah, got it right there. C is measured in farads, capital F. A farad is a coulomb per volt. It's determined by the physical parameters, like you said, the size of it, the distance apart, and one other thing, one other aspect goes into that, what makes a capacitor good at what it does. How big the plates are, how far apart the plates are, and one other thing. What's in between the plates? We say the dielectric. Dielectric is just a fancy word for insulator. So this equation, right here, takes into account those physical parameters. C equals kappa epsilon naught. Kappa is the dielectric constant. You can look that up on a table, and it would tell you some numerical value bigger than 1 for what the dielectric, the material is in between the plates. Epsilon naught is a constant, the permittivity of free space, 8.85 times 10 to the negative 12 farads per meter. It is the ability for electric fields to move through empty space. So if there's nothing in between them, no dielectric in the middle, then the kappa value is just 1 and you can use epsilon naught. A is the area of the plates in meters squared, and D is the distance between the plates in meters. Make sense? Good? All right, awesome. Thank you. Do you want your marker back? I got some. I will, it's special. Special to you. All right. I brought with me some capacitors. You know what? Just bring it in. Bring it in.
Maybe y'all could bring it back here since I can't leave the electricity.
Oh, all right. Fine.
This is
Actually, before I do, have a seat. Before I do that, because we're going to have to relocate over there, and I want to use the board, and I don't want to go back and forth over and over again. What I'm going to make is a circuit. The circuit is going to have a battery and a capacitor. Very simple circuit. In a diagram, it looks like this. We'll know the voltage of the battery because it says it right on there. It's three 1.5 volt batteries in a row. So the difference in potential between the top and the bottom is 3 sets of 1.5, which gives us 4.5 volts. So we have a difference in potential of voltage of 4.5 volts. The capacitor that I'm going to put in the circuit, it's also labeled. 470 watts.
I do that eyesight. Microfarads?
Capacitance equals 470 microfarads. Question 1, how many farads is that? So micro is 10, you're correct. Micro is 10 to the minus 6, so it's 470 times 10 to the minus 6 farads. And if you want to move this decimal spot 2 spots over, it would be times 10 to the minus 4th. It doesn't make any difference to me which way you do it, which way you write it, but it should be in farads. Thank you, thank you. If I touch this capacitor onto the positive and negative terminals, it would be like completing this circuit. I'd be connecting the positive terminal of the battery to the left plate of the capacitor, and the negative terminal of the battery to the right plate of the capacitor. Yeah? Cool. What would that do to the capacitor?
Would it charge the capacitor?
It would charge the capacitor, yes. By connecting the positive terminal, I'm going to pull electrons off of this, making this side positively charged. So I'm going to push electrons onto this side, making this side negatively charged. And it's going to charge it up. Do you know how much charge is going to go on there? Well, 4.5 is the voltage, but you're on the right track. That's something we'll need to know. Everything attached to this positive terminal is going to be at the same level of potential. So, what did I put the marker here? It's also blue. That's not going to work.
Is it black? Yeah, you do it.
We're going to go pink. Everything attached to the positive terminal by a wire is going to be at the same level of potential. So if the bottom side, if we call that our 0 point, if that's the ground, then this side is 4.5 volts higher, 4.5 volts up from that. Everything attached to the negative side, we'll use the black side of the marker. Everything attached to the negative side is all at the same level of potential. So if this is 4.5 higher than that, what has to be true about the difference in potential between those two sides? Everything in pink is at the same level of potential. Everything in black is at the same level of potential. This is in pink, this is in pink, this is in black, this is in black. What has to be true about the difference in potential between those two plates? Equal to? I don't think I understand what you're saying. I think you're on the right track, and I think you're thinking right, but I don't think you're saying it right. V across the capacitor is going to equal V across the back, equals 4.5 volts. The difference in potential across the sides of the capacitor when it's attached directly to the battery is going to equal the difference in potential across the battery. This is only true when it's the only thing attached, but in this case it is the only thing attached, so it is true. It has to be. If this is the top of the hill and this is the bottom of the hill, if I go on this path, I get to the bottom of the hill, so I must have gone down a hill somewhere. The only place it could have happened is here. So the drop across this has to be 4.5 volts. I have to get back to the bottom somehow.
Just questioning, because on our lab, doing like the simulation, you can move it was 1.5 volts and negative 1.5 volts, and you can change like the positive and negative side. Just out of curiosity, when like drawing this, is the longer part of the battery typically the more positive side of the
Yeah,
short?
this is the positive side.
Okay.
Not typically, always.
Okay.
That's what it represents. The long line is positive, the short side is. If you see one drawn like this, where there is another short and another long, that means there's more than one battery in the set. So if I was technically drawing the one that's in my hand, which I couldn't find, I would do 3, because there's 3 batteries. Make sense? Now that I know the voltage across the capacitor and I know the capacitance of the capacitor, can you figure out how much charge is on that capacitor? Yeah? How?
Is it multiply the capacitance by the voltage?
Why would you do that? You're 100% right. Why would you do that?
To rearrange the equation?
That equation over there, right? C equals Q over V. If I know C and V, I can find Q. Multiply the V up to the top, like you said. Q equals C times V. Awesome. Do it. Give it a try. Do my neck track. Do you hear it? Stiff. What'd you get?
2.12 times 10.
So 0.002-ish coulombs of charge?
Yeah, 0.002.
Awesome. That's the most basic. Now that is one of the things you're going to do in lab tomorrow. I want to show you how you're going to do some measurements in lab tomorrow. The more experience, the more times you hear this, the better off you're going to be, because the lab practical is like 90% using this device. So if you know how to use this device, you're going to be better off. If you don't know how to use the device, you're going to be in trouble. So I'm going to help you, Dr. Treese is going to help you, and if you hear both of our voices, you're more likely to have a better understanding. So this is where we're going to gather around. We're going to go up there by the camera so she can see. All right. These things are called snap circuits. Joey loved them. He probably still does, but I got him a set when he was a kid, a little kid. He's still a kid. He's 13. But when he was small, he played with them all the time. It might seem kind of, I don't know, elementary, but the way we used to do it when I was in college was we had these things called breadboards that were just like a bunch of little holes in a circuit board. And you'd stick the metal ends of the resistors into it, you'd stick the batteries into it, and you'd have to connect wires to connect across. And as they got older, they would corrode, and it was harder to make good connections. So you get a lot of error based on bad connections in the circuit board. This eliminates that. Like, you just don't have that problem anymore. So instead of having to figure out where the error was coming from, we just eliminate the error and use these cool things. Plus, they're super fun. They're like Legos. Like you build different tracks and snap them together. And, I don't know. I enjoy it. I like playing around with these too. You can make kind of neat circuits with them, even with very simple components. Right, we have a 4.5 volt battery, like I showed you. We have a couple of different capacitors. I talked to you last class about the AED device, and I said that you have a battery in the AED device, you have a capacitor in the AED device, and then you have leads across a person. That person becomes the resistor in the circuit that you're dealing with. Resistor, if you see the sawtooth, like sharp tooth pattern there, that's the symbol in circuits for what a resistor looks like. It's measured in ohms. Meditate on that. Ohms. Capital Greek letter omega, it looks like a horseshoe, that's a symbol for ohms. We'll talk a lot about resistors in the future. You need to know about this for tomorrow's lab. Essentially, we're going to be building the equivalent circuit to an AED. I'm going to put the capacitor near the battery so that I can connect the battery in order to charge up the capacitor. And I'm going to connect the other side of the capacitor to a resistor, which would be like the person whose heart is getting defibrillated. Snap them together, snap them together. Currently, there is no current moving through the circuit, and the capacitor is not charged up. But if I do connect the terminals of the battery to the ends of the capacitor, it will charge up, and then I can discharge it across the circuit. So when I connect it, it'll charge the capacitor, and when I let it go, it'll discharge the capacitor. When you do this in lab tomorrow, you're going to see a really cool curve that looks like this, an exponential curve. You haven't got an exponential curve before, e to the power something something. This kind of circuit is called an RC circuit because it has a resistor and a capacitor in it. You're going to use this device tomorrow, but only for one thing. You're going to use it in the practical for a bunch of things. It's called a multimeter. I think I told you that before, but I'm going to tell you again. A multimeter measures many things. Multi means many, meter means measurements. It can measure a bunch of different stuff. One of the things it can measure is the capital Greek letter omega, which stands for resistance, ohms, right? Stands for ohms, that's the unit for resistance. You are both correct. If you are measuring resistance, step one, make sure that the red wire is plugged into the red hole that is the ohms label on it. See the ohms label there? See the ohms label there? If it's in the other one, the white hole here, that is for measuring current. That's why it's labeled milliamps. It also above it, what does that say above it? Fused. There's a fuse inside of here, and we're going to talk about why that's important later, like what about the current requires this to have a fused component in it. But suffice it to say, the resistance internally on that fused port is very small, and if you have any kind of substantial voltage that you're measuring, the current will be way too big because the resistance is really small, and you'll blow the fuse. And when you blow the fuse, it stops working, and you won't be able to get any data in your lab practical, and you probably won't do very well if you can't get any data. So I'm going to save you that trouble. You can't really break the device if it's in the red port. You can't measure current either, which you'll have to do in the practical. But for today, we're not doing that, so keep it in the red port. For tomorrow, too. The only thing you're going to actually have to measure is the resistance. I'm going to show you how to do that. I'm also going to show you how to measure the voltage, just so you know how to do it for future reference. Sound good? Questions so far? So to measure resistance, step one, make sure it's in the red port, because that's the one that measures resistance. The internal resistance of the meter, when it's in that port, is really, really high. So you can't really break the device because you can't get very much current through it because the resistance is really big. It resists the flow of electricity through it, so it won't break. Step number two, we're going to turn the dial to the ohms section. Now, the dial has a bunch of different spots on it in the ohms section. Those spots, those numbers, represent the highest value it can measure in ohms. So the biggest one is 20 mega ohms. Capital M is mega, it means 10 to the 6th. Mega means a million. So if you play the lotto and you play the mega millions, that should be a million million. So that's false advertising, because it's not. Just now you know. 20 million, that's a really big amount of resistance. The next one is 2 mega ohms, 2 million. The next one is 200K, 200,000 ohms. The next one is 20K, then 2K, then 200 ohms. I don't know why they use 2 as the scale, but I mean they do. This device is scaled that way. If I have it set to the 20K, the biggest measurement I can make would be 20 kilo ohms. Anything bigger than that, it won't read. It'll read smaller up to a certain point. The benefit of going to smaller scales is you get more significant figures. So this one, we know, is supposed to be 1,000 ohms, 1 kilo ohm. It says it right on the label. Also, fun fact, see those colored lines on the resistor? Those colored lines are a color code that tell you it's 1,000 ohms. The factory built it, they made it so that it should have 1,000 ohms of resistance, but nothing's perfect, so we're going to measure it and see what it actually is, because it's probably not exactly 1,000. If I start at the 20K, if I started at the 2 million K, or 20 million ohms, it probably won't read it, because there's not enough sig figs to even show it. It would probably read it as 0, because it's just too small compared to that scale. So that scale won't work. We have to go to a more reasonable scale. So I'm probably going to start at 20. The way this measures resistance is it sends a small voltage across it and measures how much current gets through. If it's attached to the battery, more current will get through than it expects, and you'll get an incorrect reading. It'll give you a false reading. So in order to measure the resistance of something, you have to disconnect the battery from it. Not a bad idea just to take it entirely out of the circuit. If you're measuring the resistance across some component of a circuit, then you have to disconnect the battery, just take it out. But if you're just measuring one resistor at a time, you can just take the resistor out and then not have to worry about it. So the resistor is not connected to the circuit. So now I can measure its resistance. This is a super common mistake, and you're going to feel really dumb if you do it. I've had lots of people in lab go to measure, they turn it on, they set it to the right part of the dial, and they touch the two sides, and they're like, it's not working. And they try all the different points on the dial, and they say it's not working. Well, it's not working because there are caps. There are plastic caps on the leads. If you don't take them off, it won't work. It's happened so many times, I can't tell you, and like the person's always embarrassed and feels bad. I feel bad, but you won't make that mistake, will you? No, you're not going to leave the caps on. All right, so I'm going to put it to 20, even though I know that's pretty big compared to my 1K, and I'm just going to see what I get. It's reading, what's it reading? Can you see that?
1.0.
1.00 kilo ohms. It gives me 2 sig figs, and it's saying 1.00 kilo ohms. The unit is on there. Make sure when you're doing your practical, make sure you pay attention to what unit it's giving you, because it doesn't always give you the same unit. Different parts of the dial give you different units. If I turn this way up to the top, it's no longer in kilo ohms, now it's in mega ohms. So you got to make sure you're writing down the appropriate unit as you're answering, or else Dr. Treese is going to take points away. Now, 1.00 is fine, but I can do better, because the 2K setting is more than 1.00 kilo ohms, and I can get more accurate with more significant figures, so I'm going to do that. I turn it to the 2K, measure it, and I get
1.02 kilo ohms.
yeah, 1.020, because we paid for that sig fig,
Good answer.
kilo ohms, or 1,020 ohms. It's more accurate. If I go one more down, the top that it can read is 200. 200 is less than 1,020 ohms, so it probably won't be able to read it. I try it anyway. No, can't read it. So that 1 means it's too much resistance for that scale. I have to go back up, and that's the best I could do. Make sense? That's the most significant figures I can get out. Good? All right, cool. To measure the voltage is very similar, actually, except I want the voltage connected to the circuit. So if I want to measure the voltage, let's say, across the resistor at this point, I keep the red in the red port because it's also labeled volts. Volts, ohms, and hertz for frequency. I turn the dial to the V. There's 2 different V's. V with the straight line is direct current. V with a squiggly line is alternating current. This is a direct current because it's a battery. Batteries just send the current one way. AC, alternating current, means that the voltage is oscillating between positive and negative. Not a battery, but our lights oscillate back and forth. The outlets on the wall oscillate back and forth between positive and negative. They oscillate 60 times every single second. So it goes positive, negative, 60 times every second. These lights are actually blinking. If you have a high-speed camera and you record it at the right frame rate, you'll see a strobing effect. When Joey was little, he used to jump in the swimming pool in swim practice, and he'd have me record him in slow motion so he could watch it later. And the pool lights would look like a strobe in the room. You wouldn't see it normally because your eyes don't perceive, your brain isn't fast enough to perceive 60 blinks, 120 blinks every second. It's blinking too fast for us to notice. But that high-speed camera, the frame rate, some of those frames were totally dark because the lights were turned off, which is kind of cool. Like, it's wild that that's happening right now. We are not capable of seeing. Mind-blowing, really, because there's other stuff in the world that's happening that we can't see too. Yeah? Mm-hmm. Yeah, okay. So to measure the voltage, I'm going to turn it to, since it's a battery, DC volts. Same deal. The 20 means the biggest it'll measure is 20 volts. The 2 means the biggest it'll measure is 2 volts. I can put it up to 200 if I want. It can measure up to 200 volts. If I put this across the implement, if I get a negative number, that just means that I have the leads on the wrong side, but it makes no difference at all. If I put it on the other side, it's the same number, just positive instead of negative. Because these are all connected by wires, anywhere on there is going to be the same amount. Since this is a 4.5 volt battery, I expect it to be 4.5 volts. As it turns out, when you're sending voltage out and have a current going through the battery, you have a slight resistance internally in the battery. And the more current you have, the less it's actually going to read. So that's a possible source for error if you ever have to write down error analysis in your lab. We'll talk about why that is when we get to Ohm's law in a week or two. If I disconnect it, it should read much closer to the 4.5 volts. There you go, 4.4. But I can do better than that. I can get more sig figs if I put it to the 20. 4.50. If I go to the 2, nothing. 2 is too small because 4.5 is bigger than 2 because that's how numbers work. So the best I can do is up to 20 setting and I can get 4.50. Make sense? Okay. Very quickly, I'm going to show you the dissipation, the charging and dissipation of charge from the capacitor. I'm going to charge up the capacitor, and I need somebody to measure the voltage as we go, and then I'm going to discharge it, let it go, and you'll see the voltage drop. Tomorrow in lab, you're going to use capstone and voltage sensors to do this, and it's going to make that really nice exponential curve down. What I'm trying to show you is that charging is very fast, and the discharging is very fast. If I have this battery connected, that voltage was constant, right? It was steady. It wasn't really changing. But when I discharge the capacitor, it's got a finite amount of charge stuck on there. So it's going to discharge very quickly, which is the whole point of it. You want to be my... All right. So just touch across, either across here or right here is a good spot. It really doesn't matter. Anything connected by a wire is at the same level of potential. Right now, the potential... No, stay there. The potential difference is 0 because it's not connected to the battery and the capacitor has already been discharged. But if I touch this here, it's going to charge up the capacitor almost instantaneously. Look at that. 4.4 negative because they're on the wrong side, but it doesn't matter, you don't have to switch it. 4.4, 4.37, 4.44. All right, so it's charged up. I'm going to let it go and it's going to discharge. It's going to discharge really quickly. And it's back to 0. Good? All right, head back to your seats.
She had a question.
Oh, who had a question?
I just have a quick question. This is just to wrap my brain around it. I thought capacitors are supposed to hold charge, so why didn't the charge?
Because I gave it somewhere to go. It holds charge until you give it a... If I touch the capacitor to the battery, it'll
Yeah.
hold that charge until I connect it to the resistor.
Oh, okay, yeah.
That's a great question.
Let me reenact it.
Now, that's about the smallest bite you can take and make sense of the circuit, because it's just one thing, right? One capacitor, one resistor, one battery. But most of the time, like if I took your computer there and I smash it on the ground and look at the circuit board, I won't look for it. But if I did, for science, it would look much more complicated than one thing, I think, yeah? In fact, they get very complicated. But nevertheless, even as complicated as they can be, they're still based on the fundamental principles that we're learning right here.
So would you ever use a resistor like in a circuit?
Oh yeah.
Okay.
So we want to control the voltage and current through stuff. If you can't have as much current as you want, there's resistors in pretty much all circuitry. If you opened up your computer, you'll see resistors in there. You'll probably see capacitors in there too. So yes, you do. So one thing is the smallest bite you can take, but in order to understand how these things are interacting with each other, we need to take slightly bigger bites. But if you take too big of a bite and try to look at the whole circuit all at once, it won't make any sense at all. So instead, we look at combinations of things in circuits in the smallest bits that we can. And those organizational schemes, those smallest bits, come in two different flavors, either series or parallel. I can have implements in my circuit either in series with each other or in parallel with each other. Now, once you look at the big circuit, you'll have combinations. You'll have sets of series, sets of parallel, and you'll have those things in series and parallel with each other too. We're going to talk about those combinations at the beginning of next class. But for now, we're just looking at those bits, those chunks. So a series of circuits, implements, means that they're in a row. They're sequential. If I have capacitors that are in series, there's one path through that circuit. Let's say I have 3 capacitors and I put those 3 capacitors in series, it would look something like this. This is C1, this is C2, this is C3. Capacitance 1, capacitance 2, capacitance 3, they are in series, there's one path. No junctions, no splits, one path to go through. If these are different capacitances, they're different capacitors, well, let's say that they are for now. They don't have to be, but let's say that they are, because there's nothing that says that they have to be the same. This is a little counterintuitive, but it's true. By putting capacitors in series, I reduce the overall capacitance to less than the smallest one. Let me say that again. By putting these three things together in the circuit, the total capacitance has gone down. It's less than the smallest one in the series. Let me explain to you why. I gotta be a little bit fast because we have a whole nother thing to talk about after this. Let me explain to you why. If I connect this to a battery, the battery has a voltage, we'll call it V sub B, voltage of the battery. It's got a positive terminal, it's got a negative terminal. That positive terminal is going to pull electrons. There's either an insulator or a gap in the circuit right here, and right here. So electrons can't move across that gap. They can't move across this gap, they can't move across that gap. But it can pull electrons off of this plate. It can pull electrons off of that plate, leaving this plate positively charged. If that plate is positively charged, it's going to pull electrons towards it, but it can't pull electrons towards it from this because it's pulling just as hard. So instead, it's going to pull electrons towards it onto this plate. Leaving that plate negatively charged. Now those electrons, charge is conserved. They have to come from somewhere. They don't just appear out of nowhere. Where can this plate pull electrons from? What's the only thing attached to it? What's attached to this plate? This plate. That's the only thing that's attached to it. So it has to pull those electrons from it. Every charge on this had to come from that one. So whatever charge I put on that right plate of the first capacitor has to come from the left plate of the second capacitor, leaving that second capacitor with a positive charge plate on that side. Same thing happens. It can't pull electrons from this because those electrons got pulled away from it in the first place, so it's going to pull electrons onto this plate. Those electrons had to come from this plate, which is going to pull electrons towards the far right plate from the battery, the negative terminal of the battery. Because this is how they charge up, it's limited by the smallest capacitor. Whatever the weakest capacitance is going to be the limiting factor because it won't take on any more charge at a certain point. That being said, since this got all its charge from that one and this got all its charge from that one, the charge on the capacitors we'll call Q1, Q2, and Q3 all have to be equal. Q1 equals Q2 equals Q3. If I know Q1 and I know C1, there's one other thing I can figure out. If I know Q and I know C, what can I figure out? V. I can figure out V. V1 is going to equal, multiply the V up, divide the C over, Q1 divided by C1. V2 equals Q2 over C2. And V3 equals Q3 over C3. Two more pieces, then I got to go on to the parallel set. Remember what I said before, this is the top of the hill, this is the bottom of the hill, and I'm getting to the bottom of the hill, but this time there are 3 steps. I go down a step here, I go down a step here, I go down a step there. This step is equal to V1. This step is equal to V2, this step is equal to V3, but the total of those 3 get me back to the bottom of the hill. So that tells me that VB is going to equal V1 plus V2 plus V3. Oh, do you see that? Good. If I want to find the overall total capacitance for all 3 of these together, I can do that. The math is a little tricky, but I can do it. We call that overall equivalent capacitance. We can label it whatever we want, but I'm going to call it C123. And to find it, to find the combination of those 3, I use this equation. 1 over C123 equals 1 over C1 plus 1 over C2 plus 1 over C3. I'm warning you right now, somebody in this room is gonna make this mistake, and I'm telling you now, so I have the right to like laugh at you when you make this mistake. You're going to put 1 over C1 in your calculator. And you're gonna put 1 over C2 in your calculator, you're gonna put 1 over C3, and you're gonna add those three things up, you're gonna put that as your answer. You're gonna move on to your next question. And you're gonna get it wrong. Because that isn't your answer. You put this in your calculator, plus this in your calculator, plus that in your calculator, and that equals 1 over your answer. So what do? You take 1 divided by the thing you get, and you get this. 1 divided by this whole thing is C123. Because math.
That doesn't even work for you, so just, in my head, math on this, just, if I was using my calculator, I would just put 1 over C1 parentheses plus 1 over C2 parentheses, but,
That would give you this, right?
yeah,
Which is equal to 1 over the thing we want.
yeah.
We want this. We have to solve for this.
Oh, and then so you get that answer and then divide it again, 1 over.
1 divided by that.
Oh, okay.
I knew you were close.
I was like, math is-
All right, I got like 3 minutes, so I gotta hustle. The other organizational scheme is parallel. Parallel has a junction. Parallel has a split. This would be C1, this would be C2, this would be C3. When you put like old school Christmas lights on the tree, if one of the lights went out, the whole strand went out, because those are wired in series, and by breaking the series, you break the whole thing. In this case, there's a junction, there's a split. The charges can go different places. And they don't need each other, these capacitors don't need each other to charge up. They can all charge up at the same time. So as such, when you put them in parallel like this, the overall capacitance goes up. We increase the total capacitance because I can charge this one, and this one all separately.
Do you charge at 1/3 the rate, or do you charge at the same speed as they went?
They charge at the same speed because when I connect it to a battery, they are all connected to the battery. The positive terminal is connected to all 3 of these sides, and the negative terminal is connected to all 3 of these sides. So, VB, in this case, is going to equal the voltage across C1, voltage across C2, and the voltage across C3. So, V1 is going to equal V2, is going to equal V3. All right. Now we know the voltages because everything that's connected on this side is at some potential. Everything that's connected on that side is at some potential. So we know the difference in voltage across them, and we know the capacitance, we can figure out the charge on it. Q1 will equal C1V1. Q2 equals C2V2, and Q3 equals C3V3. To find the overall equivalent capacitance for this is super easy. C123 for a parallel set is just a sum. C1 plus C2 plus C3.
Will this be number?
Yep. It's not that bad. What?
On a question, if we get a problem, would you tell us like C1 on the capacitance for a parallel, or would it just be like already semi-drawn out?
No. I'm not sure what it's like. Other questions? Okay. Have a great day. See you guys on Friday. Thank you for the use of different markers. That was awesome.